All right, thanks for having me. FFT is great. I'm looking forward to the talks. SqueezeFit. We're going to talk about SqueezeFit. Most of you have never heard of SqueezeFit, so listen up. Here it comes. Some sponsors. These are my co-authors. Culver was a master's student in ECE, Electrical and Computer Engineering. He's great. Soledad, she's a postdoc at NYU. She's also great. Highly recommend working with these people. Does anyone here not know what compressed sensing is? Great. So a decade ago, we learned that we could completely figure out what an image looks like by sampling it at only a few locations in like a Fourier domain or something. Exact recovery. So I know what every single pixel of this image looks like after only looking at a few samples. So in the real world, we don't necessarily need to know what every single pixel looks like. Sometimes we just need to be able to classify. Is there a tumor or is there not a tumor, right? Is there something of interest in this scene or isn't there? Lots of people care about this question. We want to answer it. So cat versus dog is the cartoon version, okay? How do we find good samples that allow us to distinguish between cats and dogs? So for compressed sensing, in order to figure out which point on a given manifold we are, you want to take a number of samples that's kind of like the dimension of the manifold, or twice the dimension, whatever. Can we get away with even fewer? I mean, I want to know if it's a cat or a dog, so like 1 bit, right? Maybe there's one measurement that can separate them. Like, if I can predict that a whisker would be in this pixel, then you want to look at that pixel, and that'll tell you yay or nay. We can get away with fewer measurements intuitively because we're okay with confusing cats. It's okay if cat 1 and cat 2 look the same from our sensor's point of view. What we don't want to do is confuse a cat and a dog. Okay? So used to be we wanted to make sure that sufficiently sparse vectors avoid our null space. Now we want to ensure that differences between cats and dogs avoid our null space. Okay? It's kind of a different problem. There's been some work on compressive classification, and they all kind of do the same thing. First, they say, suppose the set of cats and the set of dogs were both from a class of sets that are interesting. Like maybe they're both low-dimensional manifolds. Okay? So if they're low-dimensional manifolds, how many samples do I need in order to keep the manifolds separated? Maybe there's a Gaussian model. Okay, how do I keep them separated, etc. We are going to take a completely different approach to this problem in this talk. Okay? Any questions before I tell you the completely different approach? All right, here it comes. This is a little technical, so I'm going to say this like 3 or 4 different ways to make sure you understand what's going on here. Projection, factor, recovery. Okay. We are told that there exists a subspace. We don't know what the dimension is. We don't know the orientation of the subspace. We're just promised that there exists a subspace. Our job is to figure out what that subspace is. Okay? What we receive is data that wants to be it wants to do compressive classification. Okay? So we have data. So X here lives in Euclidean space. pi is an orthogonal projection onto this planted subspace that we're promised exists. I apply pi to x, that Euclidean point in Euclidean space, and then there's an f thing that receives a member from the subspace and kicks out a label. It says, this is a cat and that's a dog. Okay, it's a labeling function. So what I'm getting is I'm getting data where the label factors through projection onto an unknown subspace. And my job is to figure out what that subspace is. I'm given a bunch of data. There's a promise that it's possible to do compressive classification by projecting onto some subspace and then classifying. I need to figure out what the samples ought to be. Okay? Compressive classification with projection factor recovery. So let's do projection factor recovery. Here's some data in R3. There are some green circles and red X's. If you're colorblind, you can still separate them. Okay. I promise that there exists a subspace such that you really want to project onto that subspace before you classify. Okay? Our job is to figure out what that subspace is. It feels like a dimensionality problem, a dimensionality reduction problem. I'm trying to find a low-dimensional subspace that does a good job of explaining the data. So if you're if you have MATLAB in front of you and you want to do dimensionality reduction real fast, the first thing you're going to try is PCA. Okay? Now, granted, PCA ignores the labels. It's just looking for a direction of maximum variance. So you could do something slightly smarter than PCA and actually take PCA of the pairwise differences of points of opposite label. Okay? So when you do that, you'll see that there's actually a lot more vertical variation than XY variation. So all of your pairwise differences all kind of lie in the, like a Z-word direction. And when you project onto that direction, you get a mess. You don't want to classify after projecting onto that. That's the wrong projection factor. You did it wrong. Don't do PCA. Another thing you could try is LDA, linear discriminant analysis. Let me tell you what LDA does. LDA pretends that your classes are each a Gaussian of its own covariance matrix. Okay, so it's centered. One's centered over here, one's centered over there, and they're shaped in weird ways. What you want to do is take the difference of the two means, so you estimate with centroids. That gives you a vector. And you might want to hit it with an inverse covariance matrix that makes it even better to regard the shapes of these Gaussians. And then project on to the span of that shifted difference. Okay? In this case, you notice the data doesn't quite look Gaussian. If it is Gaussian, there's definitely a lot of overlap. You end up with this monstrosity. You project onto that line, it's messy. You don't want to classify after projecting onto that line. What you want to do, we're back in MATLAB, okay? You can see that I made these images in MATLAB. You click on an icon that allows you to click and drag, right? You see different orientations, and then you'll find one that looks really nice because you're promised that there's a nice one lurking in here. That's effectively what SqueezeFit does. Okay? SqueezeFit looks for a subspace where after projection the data looks nice, and that's when you want to that's how you do compressive classification. That's what you should do. Any questions before I open the hood on what SqueezeFit is doing? Yes. So are there limits on the complexity of the classifier? So for projection factor recovery, the way we state it here, we black box the classifier after the fact. The way we motivate SqueezeFit, what we actually do here, we're motivated by k nearest neighbors classification, but we're not forced to use k nearest neighbors classification. Good question. Okay. So the second half of my talk, we'll talk about like real-world implementations, and the theme is going to be the reason the way SqueezeFit is not nice is that it's much slower than PCA and LDA. And PCA and LDA in particular is really good when your data is Gaussians that are well separated. So in that particular case, if you have separated Gaussians, don't wait for SqueezeFit. Just do LDA. Okay? Yes? You're going to get a lot of SVM vibes in the next slide. Yeah. Yes?
This is PCA along one eigenvector, right?
So if you were to select, maybe the person that told you that there's a hidden subspace also told you that it was a subspace of rank 2. If you were to use that, then you would get some other random direction and it would still be a mess. The issue here is that you have a lot of variation in the vertical direction, but you really want to project in the XY plane. Good question. Okay, let's open the guts of SqueezeFit. We want to minimize, we want to find the projection, the orthogonal projection of smallest rank that keeps points with opposite labels or different labels separated. Okay? We want to maintain margin while making the rank as small as possible. That's the game. So the data we receive, Euclidean points, comma, label. Okay? And Z is going to denote the difference set. The set of all differences between points from one class and points from another class. Okay? The difference set. We want, after projection, we want members of the difference set to not get too small. Okay? We want to preserve some sort of margin. So we want to minimize the rank of this orthogonal projection matrix, subject to, after I project a member of the difference set, his norm is at least some prescribed margin. That's the game. I don't know if you ever tried to minimize rank before. It's not fun. So instead, we relax. It's the thing you're supposed to do. And the relaxation is SqueezeFit. So first, we're going to observe that overall orthogonal projections, rank is trace. So we do that move. And then we relax the feasibility region to be any positive semidefinite matrix that's smaller than the identity. And this is the same as that. So SqueezeFit is useful even when this relaxation is not tight. You don't even have to round. You can still use what SqueezeFit delivers. And this is how you do it. You ready? So you run SqueezeFit and you get an optimal M. Call it M opt. We're going to look at the rank of M opt. The rank's going to be small. Call the rank R. My sensor is going to be a short fat matrix, the number of rows equals R, such that phi transpose phi equals m opt. So by feasibility in SqueezeFit, we know that the norm of phi applied to any member of the difference set is going to be at least delta. You're preserving this margin. So you can take your training set, apply the Euclidean point, apply phi to the Euclidean point to get an r-dimensional version of him. Train your favorite classifier on this dimensionality reduced data set. And then when you receive new data through this sensor you just designed, you don't have to waste time and look at all of the pixels. You can just look at R pieces of data and pass it through the classifier that you trained here. Does that make sense? Okay. I'm halfway done with my time, and I'm about to start. I have 6 minutes left? Wow, that's awesome. Cool. We're good. No, I'll do 6. So there's 2 parts to the remainder of my talk. There's theory, and then there's practice. We'll start with theory. We say data is delta fixed. If when you run SqueezeFit, get m opt, take a square root, that's kind of like that phi thing I was telling you about. Apply him to your data, the data doesn't move. So delta fixed. And then contact vectors are the shortest members of your difference set. These are the guys that are most easily confused. It's always the case that when you run SqueezeFit, the column space of the optimizer is residing in the span of your data. The reason is you're minimizing trace. If there's anything in the complement of that span, you can remove that component and decrease the trace. You can use that to prove the non-trivial direction of this equivalence. Your data is delta fixed if and only if the optimizer is orthogonal projection onto the span of the data. I really like this one. Don't bother running SqueezeFit twice. You run SqueezeFit, you apply the square root of the optimizer to your data, then the result is delta fixed. So if you were to try to squeeze it further, you wouldn't get anywhere. Okay? For finite data, meaning for all the data you're ever going to deal with, your data is delta fixed if and only if the contact vectors do this nice geometric thing where they span your data. Okay? This isn't true for infinite data because you can do funny things, right? Take a limit, break something. Okay. The big picture for theory is that we can prove variance of this meta theorem, which says that suppose your data is well behaved when you project onto the planted subspace, whatever that means, and also that in the complement of that subspace, the deviation from the projection is independent of where you are in the subspace, whatever independent means. Then you do projection factor recovery with SqueezeFit. Okay? So 2 instances of this. One's easy to prove. One of them's less easy to prove. In this model, by independent, we mean that for every data point in the subspace, we have an identical copy, like we're taking a Minkowski sum with a fixed set in the perp space, and we have that data available to us. It turns out that when you do SqueezeFit for this Minkowski sum, you can express it as a relaxation of the original, like if you were to get the delta fixed data in the T part, and the result falls out. What I'm interested in is explaining the phenomenon I showed you here. What I did here was I had data in concentric circles, and then I added a Gaussian in the vertical direction to each point. And I got what appears to be exact recovery. It's actually approximate recovery. I can get exact recovery if at each point I drew like 5 Gaussians. Okay, so I have 5 Gaussians in the same line, but the Gaussians in this line are different from the Gaussians in that line. So that's how this is different from the previous result. I'd like to be able to prove that for 1 Gaussian, I can get approximate recovery, but that will not use a dual certificate proof like this one did. Okay. So the dual certificate proof, it just opens up your favorite papers in the literature and uses the technology. Okay? So SqueezeFit in practice. Questions about the theory before I show you the practice? 3 minutes? What do I have? Okay, I'll get it in 3. In the real world, you're going to have like outliers. How do you deal with outliers? You fix SqueezeFit. You make it robust to outliers. So this constraint you lump into the objective the obvious way. You might want to have more control over the number of measurements you take in the end. You want to control like the rank or something. So you can throw this objective into the constraint and start twiddling with that. There are other interesting things you can do. One really good thing is you can impose that M is diagonalized by a certain basis of interest. So one basis that would interest this conference would be the Fourier basis. Another important basis is the identity basis. So if you want to restrict your sampling to particular coordinates, and this happens a lot where I want to do feature selection, you can impose that M is diagonal, and then the semidefinite program turns into a linear program. It's much faster to solve. You do this on MNIST. Since semidefinite programs are slow, we selected 50 points and have them call the shots on what the projection should be, and everybody else fell in line with them, so that you're separating green from red despite only seeing 50 data points. So it generalizes. And you can classify, and it does well, like the boxes are the errors. It's kind of weird. You're classifying based on these smudges. I look at the smudges. I can't tell what's a 4 and a 9, but K-nearest neighbors can. It works. There's a number out of range. Some people want to cure cancer. In that problem, you want to thumb through what are the genes out of these thousands of genes that predict whether you're a cancer cell. So how do I do feature selection? So in that case, you do the diagonal constraint where it turns into a linear program, and you can actually solve it with thousands of genes. And the preliminary stuff suggests that it's pretty useful. More to come on that. There's a lot of open problems to solve. I hope you're interested in solving them. There's too much for me. And that's the end of my talk.